Okay, now we will see the most important bit, design of a surge tank. Okay, so in design of surge tank there are two important aspects. One is the height of tank and second is the cross-sectional area of the tank. Okay, out of which height is much more important and the cross-sectional area, it can be decided easily. Okay, that we'll see later on. First, the height of the tank. Okay, so the height of surge tank can be decided once the maximum upsurge or downsurge are known. So upsurge is the height at up to which the water level will come up. Okay, so expression for maximum surge, so this is necessary for designing the height of a surge tank. Okay, this expression is derived with help of continuity equation and momentum equation. Okay, so this will be the diagram. Okay, so AS, area of cross section of a tank. So see this diagram, this we have seen it earlier as well. So this is the storage of the water, reservoir, pipeline, this again pipeline, this is turbine, TWL. Okay, so this line is static head, this is reduced head, this is increased head, and this is HF. Okay, HF is generally neglected here. Okay, so cross sectional area of this tank is AS. Okay, AS, area of cross section of the tank. A, area of cross section of the pipe. Okay, this pipe I am talking, the low pressure pipe, or which is upstream of the tank. This is upstream. Okay, then length of the pipe, again upstream. Okay, velocity of flow in the section V in the upstream pipe. Okay, and V0, initial velocity of flow in the pipe in steady state condition. Okay, steady state condition, when there is neither much increased demand or reduced demand, the velocity of flow is called as V0. Okay, so we know now V0, VA, L, and this AS. Okay, with this we will decide the expression for maximum surge. Okay, now loss of head due to friction, HF, in the pipe is neglected in the design, so HF is 0. This I already told you, this HF is treated as 0. There is no head loss in the low pressure pipeline. It is assumption. Okay, HGL line is horizontal line with static liquid level. So this line is horizontal with this static liquid level. Okay, when the wall is closed suddenly, liquid level in the surge tank rises Z above the initial level. So initially the water level was here. When the wall is suddenly closed, water level rises a Z distance above. Okay, now applying Newton's second law. So rate of change of momentum is equals to force, and this is the Newton's second law. Now rate of change of momentum is mass into acceleration. So acceleration is change in velocity divided by time. So this is written as mass in of liquid in pipeline divided by time into change in velocity. Okay, so this is it, rho al, mass of liquid, into dv by dt. This is momentum, and this is equals to force A, cross sectional area, into gamma into z. Okay, so minus sign because this rises uh, it rises when the flow is taking place. Okay, so dv by dt is upon simplifying, a is common to the both sides, it is cancelled. Dv by dt is minus g into z by l. Okay, so dv by dt, dv by dz into dz by dt, okay, is equals to minus g into z by l. Name this as equation number 1. Okay, so purposefully we have introduced here z, chain rule. Instead of dv by dt we have written dv by dz and again dz by dt. Okay, so now dz is the rise in liquid level in the surge tank in time dt. Okay, by applying continuity equation, volume of water flowing into the pipeline uh, in time dt is equals to volume of water stored in surge tank in time dt. Okay, so volume of water flowing through the pipeline, it is A into V into dt. area of cross section of the pipe into velocity into dt is equals to as into dz. Okay, so upon rearranging, dz by dt is equals to a by as into v. Okay, substituting the value of dz by dt, this dz by dt is equals to a upon as into v in this above equation. Okay, so what we get, dv by dz into dz by dt, instead of dz by dt I have written now a by as into v minus g into z by l, so same as that. Okay, so now I am interested in dv by dz. So dv by dz is equals to, taking these terms to the right hand side, minus of as by a into other bracket g by l into z by v. Okay, now bringing z to this side, so or dz to this side, z into dz is equals to minus a by as into L by G into V into dV. It is just rearrangement of the terms so as to bring Z and dZ onto the same side. Now you might guess what we will be doing next. It is integration. Integrating both the sides. Here Z dZ is there and here V dV is there. We can integrate. So Z square by 2 is equals to minus of A by AS is a constant, L by G is again a constant, and V dV, V square by 2 plus C, constant of integration. Next, to find the constant of integration C, use the initial conditions, where that is Z is equals to 0 when V is equals to V0. Okay, so rise in water level is 0 when the water is flowing with the original velocity. Okay, so we get C as this, V0 square by 2 into bracket A upon AS into L by G. So this is just value of C. Okay, now substituting value of substituting value of C in above equation and rearranging, what we get is this, Z square by 2 is equals to V0 square minus V square by 2 into A by AS into L by G. Okay, again rearranging, we get expression for Z square as V0 square minus V square into A by AS into L by G. Okay, name this as equation number 3. So from here we can find out expression for Z as square root of all the quantities on the right hand side. Okay, now the velocity of flow in the pipe will go on reducing from V0 in the beginning to 0 at the end. Okay, when the wall is closed, liquid level in the tank will go on increasing from 0 in the beginning to Z max at the end. Okay, maximum rise in water level in surge tank is Z max. It will occur when the wall is completely closed, that is V is equals to 0. Okay, maximum surge is given by, okay, so maximum surge we can find out as Z max, and Z max is equals to when V is equals to 0 in this expression. Okay, so it is Z max is equals to V0 into under root of A by AS into L by G. So this is the height of maximum surge. Okay, now next thing is the time required for maximum surge, maximum upsurge. Okay, we know that dz by dt is equals to A by AS into V. This we have derived just now here. Dz by dt is equals to A by AS into V. Okay, now so dt is equals to A by AS into 1 by V into dz. Okay, but from equation number 3, this equation, okay, we can write V square is equals to V0 square minus AS by A into G by L into Z square. Okay, so V is equals to square root of V0 square minus AS by A into G by L into Z square. Okay, substituting the value of V in above equation and integrating, what we get is dt equals to as by a into integral of dz divided by square root of v0 square minus as by a into g by l into z square. Okay, so upon integration we get t as equals to integral of as by a into l by g outside the square root sign, outside the square root sign, sine inverse of z by z, z upon z max. Okay, so the time required for maximum surge is T is equals to T max, and when Z is equals to Z max. So T max is equals to square root of as by a into L by g into sine inverse of 1, because Z is equals to Z max. Okay, sine inverse of Z max upon Z max, that means 1, sine inverse of 1. So sine inverse of 1 is pi by 2. So T max is equals to pi by 2 square root of as by a into L by g. So this is the time required for maximum upsurge. Okay, next important thing is the cross sectional area of the surge tank. Okay, now the actual practice, cross sectional area of the tank is decided as factor of safety multiplied by minimum cross sectional area required. Now the minimum cross sectional area required for the tank is given by as minimum is equals to v square divided by 2g into LA divided by HFO into bracket H minus HFO. So HFO, head loss due to friction in the initial stage. Okay, thank you.